Greetings and welcome to another C# coding session. On Wednesday I had a slight schedule mix-up. It will happen every now and then. I do apologize about that, but it can't exactly be helped. I have a future event that I can't move from a streaming day to a different date because of healthcare system scheduling. So I believe it's on the Friday, the 1st of June, I will not be able to stream either. Because of that, I'm helping someone with some things with the Danish healthcare system. So it'll be another instance where I won't be able to stream, but I'll make sure to post it on the Twitch page as well. Okay, so last time we started building some custom font rendering stuff to support the custom colored messages and stuff for things like restart warning messages and such. And today we are going to continue working on that and possibly do a little bit of code cleanup, getting things organized a little better. It seems to me that I've been neglecting organization a little bit, so we'll be looking into that as well. Before we get started with all of that stuff, though, I think I'll grab the, let's see, the main forum right here. And right, we do have a test button down here, which currently just dumps a randomized message. I think I'm gonna change this to pop the CustomText dialog. So we've got a testing / debugging point to properly test that the glyphs are rendered correctly. So let's, yeah, I guess we'll just comment this out for the moment, like so. Just so we can pop the dialog instead, and then take it from there. So for that we are going to need the CustomText dialog, and fire up a fresh one of these, and then let's see, did we put in a property for yes, we did, CustomText. Let's put something in there. Schedule server restart in, yeah, I guess we can use that. So dialog.customText equals this, just for the sake of testing, and then we'll show it modally and dispose of it afterwards. There we go. Now we have a test dialog that we can load up. Basically, the test dialog in its current form is just a black area. We'll be rendering the custom coloring on top of it, and then we'll add in some methods for, or some custom button style thingies to do the color selection and bold and strike through and underline and all that stuff. But at least now we have a foundation for doing some rendering tests. Get rid of chat element. We don't need the design view for this. And here we go. Okay, so before we start an attempt at actually drawing some pixels onto a surface of some kind, we kind of need to know how big that particular surface needs to be. And that's exactly what measure string does. It runs through the the glyphs, and attempts to calculate the size of each glyph, including the extra space needed for rendering each glyph in bold, because that takes up one additional pixel. But one thing that we at the moment don't have as part of this glyph rendering stuff is we don't have the means to instruct the font object to basically double up on the actual font rendering. So if we quickly take a look at, let's see, do we have that somewhere? Possibly. Let's see. Yes, right here. So this screenshot basically shows the entire UI doubled up, which means each individual actually drawn pixel is actually doubled up to become a 2 by 2 pixel size. So we kind of want to set up the font rendering object to have a similar feature, and then have it produce an image that is basically twice the size as normal. So we'll add in either a property or a method for doing that. We should probably put it in as a property. Let's see, letter spacing shadow should actually be down here somewhere. There we go. And we'll do a boolean for that, double size, like so, and we'll do false by default. Alright. There's actually one thing that we do need to do, and that is to fetch the glyph texture, which is currently added to the embedded resources right here. So we'll need to fetch that and pass it to the font object. So let's see if we can get some of that stuff done. We'll grab the thingamajig from the main form, because I do believe that we have a method in here for get resource bitmap by name. Yes, let's fetch this one and add it up here. This is the CustomText dialog, by the way. Internal helper methods. Put it in here. We definitely need to be able to fetch the glyph image so we can correctly pass it to the font object to do all of the rendering stuff. All of that is set correctly. Sorry, I'm just catching up from last time. Okay, so here we need to put a reference for, let's see, private MinecraftFont, and we'll call this MCFont. There we go. Import the namespace like so, and we're good. Okay, so in order for us to set the glyph bitmap and have it converted into usable data, we need to make a call to setGlyph bitmap. So we shall do that. Let's see, we might as well just do that here. So set glyph bitmap and then get resource image by name and specify the image name from the resources, which is font glyphs ASCII. Right here, font glyphs ASCII. There we go. And that should then set the glyph bitmap to the font object. There we go. And then we can start doing all this stuff. So just to recap quickly, the setGlyph bitmap takes a bitmap and then basically processes it by copying each individual glyph into basically a bit buffer. Once that's done, it scans each individual glyph to figure out the actual width of each separate glyph, which is done by looking through these. So every time we have a solid pixel in the image, we consider that as a bit that should be drawn. And a transparent one, of course, becomes a non-drawn item. But if we take a quick look at all the letter glyphs, a perfectly good example is, for example, the colon and the I, the L, the apostrophe, and so on and so forth. They are all left justified within the actual space of the glyph itself, and the scan glyph method basically loops through the glyph to figure out exactly how many pixels that particular glyph is in width, and then stores that number for faster reference. By doing that, we can then basically use that information to figure out exactly how many pixels each individual glyph will take up, and then from there allow us to draw text that has similar spacing to what the game actually does. Of course, that requires that we implement the code, which we're about to. So we should be fine on the glyph stuff here. The measure string method right here is the one that basically loops through each individual chat element to figure out exactly how wide in pixels the drawing surface needs to be. But one thing that we most definitely will need to do is to do a little bit of text conversion, because just looping through the text itself, which is done right here, kind of ends up with some measure of error that might pop up here, because by default the C# environment runs on UTF-16 encoding, and we kind of need a pure ASCII encoding for this stuff to work correctly. Otherwise, we will run into a situation where specific characters will be converted into a question mark rather than converting them into the actual character that's available in our glyph atlas. So that's one point that we definitely need to create a fix for at some point. I know from experience that grabbing some UTF-8 or UTF-16 encoded text and using the text encoder to convert it to ASCII at times forces specific characters to become question marks, where those specific characters in reality could have been converted to proper ASCII values, which for some reason the text encoder doesn't do correctly. I'm guessing that is down to the fact that ASCII encoding kind of relies on some of the old code pages that were used in DOS to correctly encode them into the individual characters. Now, for our case, we actually do know some of these characters already, so we could potentially help the text encoder to correctly convert these into the individual glyphs that we need to reference. All of the glyphs that are read from this bitmap will be stored in the same order, meaning that each individual glyph will have its correct position, so that we can correctly index them when we need to draw them. But we definitely need to add in some amount of ASCII encoding, so I'll put a comment in here quick. Add in a reference to a better ASCII conversion for the text. That's definitely something we need to do, and we may have to build up a separate class to handle that. A static class should be able to figure that out for us, so we can do better ASCII encoding. For that, we may need to hard code or hardwire some of those conversions, but we'll get to that. Okay, for now we'll just assume that measure string will correctly measure the text, even though we do know that some of the characters will be converted into question marks. That's just how it works. Actually, this will most likely bug out. Yeah, we'll see. In any case, up here in the drawString method, this one is the one that will do the actual glyph rendering, and it is of course based on whatever chat text we throw at it, which is then converted into chat elements, so we can correctly encode each part of it with the chosen color and so on. And actually I should have brought up the wiki page that contains the colors, which I didn't, so I will go fetch that quick. The formatting codes on the official wiki, and waiting for this stuff to finish loading. There we go. Alright, so here are the formatting codes, which also contains all the colors. And for whatever reason that escapes me, those... oh, no, never mind. I'm being a derp. Alright, so... interesting. I wonder if that background color... that's probably the shading. Interesting. Alright, so we kind of need to copy over this definition of colors and then link them up with something that can convert from um, the chat element technical name into the actual color reference, and in a way where we can actually um, use that information to draw up each individual pixel as we start performing the actual glyph rendering. Now, for this to work, we definitely need some surface to draw on. So we'll create a buffer, a byte array basically, and then we'll, when we're done drawing the glyphs, we'll do a conversion like we did in the setGlyph bitmap method. In this case, we're basically copying the contents of the bitmap into a byte buffer and then processing the information by indexing the contents of that byte array buffer. What we're about to do is basically the same thing but in reverse order. So up here we will need to set up a byte array. So we'll do that. We'll call it the same thing. And this needs to be the size of the measured area that's required for rendering this text. So for that we will use the surface size width times surface size height. And again, because we're going to use a 32-bit image for proper transparency, we will need 4 bytes per drawn pixel, 1 byte per color channel, plus 1 extra for the alpha channel, the transparency channel. So we'll need to multiply that by 4. There we go. All right. So this will then house the. Actually, I'll put in some. Convert the chat text into individual chat elements. Calculate the size in pixels required to render this text. Create an image buffer. We can draw into. There we go. And then we'll go up here in the internal helper methods and add in a method for doing the color conversions. Now, if we go down here quick, I did put in a comment down here which specifies in which order the 4 channels for a pixel are arranged. And this particular order will become important when we start building up the color table. So let's build a we'll build a new method to fetch one of the colors. Get color, and then we'll add in a an extra option which lets us determine whether we are drawing a an actual letter color or if we're drawing the shading, so the background. So we'll need 2 versions of this, and both of them should return a small byte array. And the reason for that is so that we can simply use array.copy to copy in the color definition of a specific pixel into our image buffer to help us get the best possible performance out of this that we can get. So get color, and for this we could actually just pass the chat element that we get down here. We might as well just do that because in doing so we know that we will have a color reference. So we'll grab a chat element here and then use that to figure out which color to fetch. And the second version of this method needs an added argument that determines whether this should be a shadow color or not. And then we'll do all of the color decoding in this method. So we'll need a result of some kind, and for this we'll create a fully transparent black pixel as a default value, and then return that. And up here we will return get color, the element, and this will default to not being a shadow color. So if this is a shadow color, then we need to use the background part of this setup, and if it is not normal color and shadow color. If it's a normal color we need, then we need the foreground set of colors from down from this list. All right. So here we will we'll start by doing the normal color stuff. Might as well. And for that we need to fetch the element which has a property called color, which contains a string. We know for a fact that this will always be lowercase because we designed the chat converter to follow the requirements of the game and the game server and the game client. And if we go back here quick and have a look at it again, we can see that all of the technical names, which are the ones that the game and the game server requires or expects, all of these are lowercase, so we can easily use those in a switch table or switch statement to correctly find each individual color. So for black, we need to set result to a black color, break this one, and just to remind ourselves of the order, we'll go grab the comments from down here and put them up here so we know exactly which order they need to be in, like so. And this one states that the first index is the blue channel, followed by the green, followed by the red, and finishing off with the alpha channel. So when we need to set an actual color, we need to specify the last byte to be 256, which is full solid. Hey Joban. And the other channels are basically the reverse of what's specified here. So for the black, it should be fairly simple. Blue, green, red, and finishing off with the alpha channel, like so. Next one would then be fetching the dark blue, which is set to 0, 0, 170. So we need to reverse that. Nope, there's no hiding. Like so, we'll set up the color setting, and here we need to remember that it has to be in the reverse order. So the blue channel is first, which was 170, followed by the green, finishing off with the red, and then of course do the full opaque strength. Break. There we go. That takes care of the dark blue. Next up is the dark green, which is easy because the green position is in the middle, so should be fairly simple to keep that one in the correct order. Get the dark green right here and set this one up. And again, the blue needs to be turned off. The green channel at 170 and the red channel turned off, followed by full strength alpha. There we go. And next up, the dark aqua. That one needs to be 0, 170, and 170, so reverse the order again. And I see that my lovely Visual Studio has derped up again. I do love it when it does that. There we go. So blue channel needs to be 170, green channel 170, followed by the red channel, and finally the alpha channel. This should be fairly straightforward from here on. Dark red. This is going to drive me absolutely bonkers. So blue, green, red, and alpha. And the dark purple, which is the red and the blue channel. And set this up. Blue, green, red, alpha. There we go. And the gold. Now gold is a little bit different because here we're actually using a full strength red mixed with about a half strength green to get the golden color. But again, it's reversed, so it's not a huge issue. Case gold. Get ourselves a fresh bite. This would be the blue channel, which we need to turn off, the green channel, and the red channel, and then again the alpha, and we're good. And for the next one, we need the gray, which is at 170 all the way through. So that one's very easy. 170, 170, 170, and finished off by 255. And there we go. And then we have the dark gray, which is 85 all the way through. So we'll do 85, 85, 85, and 255, like so, and that takes care of this one. And the blue is up next, which takes full strength at blue and a little bit on the other ones, and finished off with the alpha. There we go. Reverse order. And the green, which is also known as lime. So that result. There we go. This one should also be fairly straightforward since the green channel is in the middle. There we go. And the aqua is then again the blue and the green at full strength, and then a little bit on the red, just to pimp it up a little further. There we go. So blue and green and red, followed by alpha, like so. And the red channel, red color, white, blue, green, red, and alpha. And the light purple, also known as magenta. New byte. Blue, green, red, and alpha. There we go. And the yellow. Yellow, there we go. Result, new byte, and this would be the blue. So for a yellow, we don't need the blue, but we do need the green and the red at full strength, and we also need the alpha channel at full strength. There we go. And finally the white, which is of course full strength on all three. So we'll put white in here, result equals new byte, and that of course then becomes 4 bytes of 256. Okay, so this should take care of handling the 16 colors. However, there might be situations where color is empty or color contains none. So to follow what the game does in terms of no color specified, which is basically what's the default setting after a reset, we will convert white into becoming our default situation instead. And just to be able to put that in here, we'll do this, which would be white. There we go. So in any situation where the color setting of the chat element is anything but anything like empty or set to none because it's been reset, or we end up with an actual white reference, we will get a white color. That's the default color setup that the game does. So this just forces a white if we can't recognize any of the selected colors. Okay, so for the shading, which would be the shadow that's shown on these color samples over here, that shading is basically the background color up here, which we will also copy. But for this situation, we've already done most of it, so we'll copy this and then simply just change the color references. There we go. So for black, well, that should be fairly straightforward. Black is black. The blue is different. Instead of 170, it's reduced to 42. So for the dark blue, we will change the blue channel, which is the first one, down to 42. And then we'll check the green, which again is reduced to 42, so we'll reduce that to 42. The dark aqua, again reduced to 42, which should be pretty much identical for all of them, except of course the gold, which will be different. 42, 42, they're all 42. So until we hit dark gray, all of them get converted into 42. So there we go. Get these converted quick. This would be the gold. So The gold one needs to be 42 across the board as well. Again, we still need the full strength on the alpha channel to get a solid pixel. Gray is reduced to 42, like so. And for the dark gray, we went from 85 down to 21. So for every case of 85, we need to reduce that to 21, and for every case of 255, we need to reduce to 63. Should be fairly straightforward. So 21, 21, 21, and this needs to be 63, 21, 21, and again here 63, 21, 63, 63, 21, and 21, 21, and 63. Whoops. There we go. And then for the yellow one, 63, 63, and finally the white, which of course should be all 63. There we go. And that one and that one. All right. So now we have a method of turning the chat element's color property into an actual color that we can stuff into our image buffer. That should then take care of handling the color settings for us. Now, excuse me. Next up, we will see about rendering this text that we've been passed. So, how do we do that? Well, we kind of need to work out a calculated position within the image because first of all we need to know the X and the Y position that we need to draw or skip each pixel on, and we need to offset that particular position by 4 bytes every time we need to render a pixel or simply just skip it. The reason for that is because each pixel takes up 4 bytes to define the color and transparency of that pixel. Just as we did when we did the glyph conversion, we did some offset calculations down here to work out exactly where to set a bit either active or inactive, and then we need we set them active here and inactive here, indicates transparent. These are the references that we basically need when constructing this as well. Actually, I wanted to grab this one. Yes. This calculation right here states that the pixel line width is basically the width of the bitmap times 4, and we need the same kind of size calculations for our image up here. So we can correctly position our draw pointer and copy the colors into the image buffer as we are building each individual pixel for each individual glyph that we are rendering. Now, we also know that we need to figure out whether we should actually, let's go up here quick. This one we need to worry about at some point. Right now it's not vitally important. Letter spacing provides the amount of pixels between each glyph being rendered, and line height determines the total number of pixels height-wise that we are drawing inside of. And as we are rendering each individual glyph, we also need to know whether we have to draw the shadows for them or not. The reason we need to know that is because when shadows are enabled, we basically need to grab the entire glyph and offset it by 1 pixel to the right and 1 pixel further down compared to where the actual foreground glyph needs to be drawn, and then effectively render the same glyph twice. One as part of the shadow setup and one as part of the actual foreground glyph itself. Now, to avoid us having to basically loop through the layout of each individual glyph twice, we will simply just do a pixel draw with a with the proper offset. So when we're drawing a glyph with shadows enabled, we will draw 2 pixels for every time we loop through a glyph instead of just drawing one without shadows. All of this, of course, needs to be positioned correctly. Hang on a second. Weird sounds in my apartment. Just a sec. Oh, somebody was drilling in a wall somewhere. Oh, okay. God, that scared me. Okay. So we definitely need to know exactly where we need to draw this stuff. We also need to loop through the glyph and then update the positions accordingly. And to draw the entire text that we have been passed, we need to loop through each individual chat element and then render each individual glyph within each individual element. Of course, also setting the correct color. First of all, loop through all the chat elements. So we'll need a loop for that, and we'll use E less than chat elements length. And this, of course, we need to do because there could be multiple elements in here that we need to process. For each chat element, we know that each individual chat element block will contain an individual color setting. So we'll grab a actually, we'll put them up here. Pixel color buffers. Do a for color and set that to nothing. And we'll do a back color. Actually, this should probably be shadow color. That's better. There we go. All right. So before we start rendering the first glyph in the first chat element, we kind of need to figure out what color this particular glyph should be drawn in. So grab the for color. For that purpose, we have the chat element that we can pass, and we need to figure out whether we should include the shadow or not. But we'll add in a check here to work that out. Let's see, chat elements, this one. There we go. Fetch the for color for this chat element. Do we also need the shadow color? If shadows, then we need to set fetch the shadow color for this element. So we'll do shadow color equals get color chat elements, and this one needs to be a shadow color. There we go. All right. So now that we've got the colors, we can start processing stuff. But we kind of need to know exactly how wide the surface size needs to be, because when we calculate the target position for each pixel, we need to know exactly how wide the image is in bytes. And to do that, we need to grab the surface size width times 4 to get the full number of bytes that each drawn line of pixels takes up. We also need some way of determining current draw X and Y positions. So we'll need a couple of variables to take care of that particular issue for us. And then we can start rendering a glyph. Though we do have a tiny problem, which is that we need to respect the individual width of a defined glyph. And since the glyph buffer is always the full size of the glyph itself, we also need to do some cross calculations to get that drawn correctly. We could put all of that stuff in here as part of this loop, but to help us keep things separated, I think I'm gonna set up a couple of extra helper methods to assist us in doing all this buffer copying and calculating the actual positions correctly, so that we can just specify the pixel X and Y positions where we want to draw something, and then specify we want to draw this particular glyph at this particular position into this buffer using this color and this shadow color. That'll make it a little easier for us. Let's see. Actually, we still need to update the X and Y positions. Nah, we'll just do it here. Never mind. All right, so we know that each chat element has a text property, and the text property contains the contents of this particular element, and that's the stuff we need to render. So we'll need to loop through each individual character of this text property, so we know exactly which glyph we need to render. So we'll loop through that. We'll use T to specify that. Less than chat elements E, and Um, let's see, that would be the text length, and there we go. All right, so we should probably also grab a couple of draw X. We'll do a draw Y. There we go. Current draw X position and current draw Y position. There we go. Now we know what they are for. Okay, so every time we finish drawing a glyph, we need to update the X position by the width of the glyph that we just drew, plus the letter spacing to get the next X position that we need to start at. The Y position I'm adding in here will probably not do much with it just yet, but the reason I'm adding in the Y position is so that we can make sure that we can support a new line definition as part of the chat text for the MOTD custom color setups for future setup. At the moment, it doesn't support it. We can put the new line, which would be that one, of course. This typical C new line indicator is fully supported as part of the MOTD text, as is evident by this sample from Applecraft, randomly chosen server, just to fetch some good examples. As we can see, it does have 2 lines of MOTD text here, including color stuff. That proves that we can actually put in the new line indicator. And at some point we will upgrade our chat converter, chat elements, all that stuff, so that we can support a new line setup as well. And in that case, measure string will end up having twice the height as the output. When we do this rendering, of course, we also need to be able to correctly Y position the text that we are rendering. That's just for future support, and also because it makes it a little easier to just have the variable that points to this particular location. Okay, so let's go down here and grab the, yeah, I know that this won't work. Actually, this has to be converted, because if this will crash if I type in, say, that character or this character or this character. And the reason it will crash is because you cannot convert a UTF-16, which is a 2-byte setup. You cannot convert that into a single byte value. That will cause a byte overflow, which of course will cause a crash exception. Here we actually do need to do a quick conversion, so we'll do ASCII text and do the text encoding, system text, actually ASCII encoding should be fine. let's see what we can get here. Nah. System text encoding ASCII, and there should be something in here. Get bytes. Yeah, we'll use get bytes. That should be enough. And that of course takes the string right here. Alrighty. Which is the elements e-text, and then this of course needs to be a byte array. There we go. Elements. There we go, and then we'll need to cross-reference this instead. So we'll use ASCII text here, and that would of course then become the ASCII text right there, and the T like so, and that should then take care of the particular issue. We still need to won't correctly convert into full ASCII, so we'll have to create a custom converter. Okay. Now at least we should be past the particular crash issue that could occur. So to get past this particular issue up here, we need to do the exact same thing. Convert the default UTF-16 string into ASCII, which of course again would be a byte array, and get bytes, which of course would be the chat elements text property, like so, and then we need to loop through this one to get the glyphs that we are about to draw. So we'll do that through each ASCII character reference, and then ASCII text length. It's driving me absolutely nuts that IntelliSense has died on me. Yeah, hang on a sec. I'll restart this thing. There we go. Okay, so this now provides a reference within the glyph chart that we can then use to figure out which glyph we are about to draw. So we'll do a glyph index and grab that from this one, and then we can loop through the glyph, drawing only solid pixels. All right, so we know that we have a couple of variables that determine the maximum size of each individual glyph in the glyph atlas, which are these two. So the glyph width and the glyph height. They determine the maximum size, and for each individual glyph we have the actual pixel width of said glyph. Those are the values that we need to make use of, and since we only want to run these particular loops for the exact number of pixels that have to be processed instead of processing the full glyph every time, which causes some excessive unneeded looping and could place our calculations outside the range of our image buffer. We need to do all the math in between to correctly scale to the actual number of pixels that we need to process. So let's see if we can get some of that stuff done. All right, so we know that we have a height of the glyphs which is identical across all glyphs. Just to recap quickly, the height of each glyph is 8 pixels for this particular glyph chart. Of course, there could be a different height on the glyph charts if, say, for example, we pass one of the Asian symbol charts. Those are, I believe, 16 by 16 pixels, something like that. Which means basically the glyph image is twice the size, which of course then, because of the way that we wrote the code, will also double up the size of glyph width and glyph height. So we need those to calculate the actual distances that we need to offset by. We also know that in order to update the Y position, we need the surface size width times 4 to move one Y position down. Okay, so we'll start by looping through the height, and for that we'll use H, and the height of course is the height of the glyphs as determined by the glyph chart. That's identical for every glyph. What's different for each individual glyph is the width of it, because some of the glyphs will basically only be 1 pixel wide, some of them 2 instead of 8. So we'll use that width to determine exactly how many times we need to loop through this. And then we'll have to calculate where is it? Let's get rid of this quick. And these. This byte array determines whether we need to draw a pixel or not, and this particular size, this particular byte array will always have the size glyph width times glyph height. So if it's 8 by 8, bits will always be 64. Instead of being, say, just 8 or 16 if the glyph is only 1 or 2 pixels wide. Hey, Pin. Good to see you. So, let's see if we can get this stuff calculated and positioned correctly. So we can get those pesky pixels drawn on our picture. Pesky pixels picture. Say that 10 times fast. All right. So for the width, we know that each individual glyph has its own width. So we'll use that. Less than, and I do believe it was called glyphs. Yep, and we have a glyph index right there, and it has a width right here that determines exactly how many pixels wide this particular glyph is. So this would be the actual loop through, which then, instead of producing 64 runs of this code, by looping through every possible position of solid and transparent pixels within the maximum glyph space, we end up only running this code say 8 times for a 1 pixel wide glyph and 16 times for a 2 pixel wide glyph. So we'll save a little bit of processing power by doing this. Alright, so here we also need to correctly calculate whenever we need to figure out whether we have to draw this pixel or not. We need to convert positioning to fit the size of this bits byte array. Remember that a pixel or a bit here that's set to 0 is transparent, and if it's set to anything else, we will accept that as a solid pixel. First of all, we of course need to work out whether this particular, which particular bit we need to check. So we'll do a byte, call it bit, and then see if we can calculate the correct position of it. And this would of course be within the glyph index, and that would be the bits. And this is where we need to do the calculations. Now, to calculate this correctly, we know that the bits array will always have the full glyph dimensions, which is of course the glyph width times glyph height. So in calculating where exactly we need to pull this out, we will grab the h variable in the outer for loop, and time that up with h times the glyph width, because each line takes up the full glyph width. So at the first line we'll get 0 because we start at 0. The second line of bits will start at 1 times glyph width. In this case it's 8, which would be the correct position for the second line of pixels. And of course here we also need to add in the current width position, so that we can get the correct offset for this. So that's the basic formula for calculating a lesser position within the full size array. And if this is for the pixel buffer, we also need to multiply by 4, because each pixel is 4 bytes. In this situation with the bits, it's 1 byte. This should then provide us with the proper bit, and then we need to work out whether this particular bit is transparent or solid. So for transparent bits, we don't want to do any further processing. Basically there is no point in copying over a transparent bit, doing the math to calculate exactly where to put this copy, just because we're putting in a transparent bit. So we'll simply just skip it. Now the reason we can do that is because whenever we initialize a byte array like this, that byte array will be pre-configured to contain all zeros. And since specifying 0 as the strength for the red, the green, the blue, and the alpha channel indicates a transparent pixel that is black, we can easily just skip that entire pixel processing if the bit indicates that this particular pixel should be transparent. So that'll save us a little bit more processing power because we don't have to do the positional math and we don't have to do the array copy stuff. In essence, drawing transparent bits will become a lot faster than doing the processing for drawing a solid pixel. Buy the efficiency wherever you can buy it, and this would be a perfect example of one situation where you can buy yourself a little bit of performance just by simply skipping on that process. If a bit is greater than 0, meaning it's anything but transparent, then we need to process it. All right, so excuse me. All right. So right now we kind of need to work out exactly where we need to draw this particular bit. We can calculate that based on our current draw X and Y positions. And the quick and easy way of handling this positioning is, of course, to add in the current height of the glyph that we're rendering, as well as the current width. These should actually be X and Y positions, to be honest. Blah, 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 blah. We'll use a GY instead. That's probably more indicative of what this actually is. And then GX here, like so. And then we'll update these, which would be the GY and the GX right here. There we go. Okay, so just for info, GX equals glyph X and GY equals glyph Y. There we go. Okay, that probably makes a little more sense. All right, so since we're dealing with pixels and we're basically going to draw these based on pixel positions, we can pretty quickly and easily calculate the pixel positions and then cross-calculate by using pretty much the same formula as this one, where we need to place the pixel color reference. We'll do, just for the sake of readability, we'll do this, which would be the pixel X equals draw X plus the current glyph X. The pixel Y position would then of course be the current draw Y position plus the current glyph Y position. And then we need to calculate where we need to place the forecolor. And perhaps to ensure that we don't get the whatchamacallums, let's see here, when we need to add shadow to it, we actually have to draw the shadow first and then the actual glyph pixel afterwards. By drawing the shadow first, we can basically replace the shadow with the actual forecolor in those situations where the solid pixels of the glyph overlap the shadow. So we need to make sure that we draw the shadows before we draw the actual foreground pixels. Draw the shadow here. We'll do that later. And then down here, draw the foreground glyph pixels. There we go. All right. So we still need to calculate where we actually need to draw this. So to help us out a little bit, we will add yet another, which would be pixel line width, which equals the surface size width times 4. This will just help us calculate the actual Y positions a little easier. So here we know that pixel X and pixel Y contain the actual position that we need to draw these in. So let's see, we'll call this target position. Set that to 0. The target position would then be, and this is again just to keep things readable. I could easily just have done something like this up here, but this is a little bit complex. So, all right. Just like we did up here, we need to calculate the Y position first. The reason we need to do that is because the Y position depends on the width of the image buffer. So here we would need to grab the pixel Y times the what's it called, pixel line width, and since this one is already upped by 4, we don't need to take that into account. But we do need to do so for the pixel X position. So we'll add, multiply that by 4, and this then yields us the position at which to draw the foreground pixel that we are currently processing. Okay, so copy the 4-color pixel into the image buffer. And the way to do that is simply to use an array copy. But we need to specify positions. So we'll grab the 4-color. We need to start at the first byte. Then we need to put this into the image buffer at the target position. And we will be copying the length of the 4-color, which is 4 bytes, as defined by the color method above. So this now copies whatever foreground pixel we have into our image buffer at the position that we just calculated, and that's basically it. So to do this for the shadow, we'll check if we need to draw it. So if shadows is true, then we need to basically calculate this, but we need to calculate it offset by 1 pixel to the right and 1 pixel down to get the same kind of shading effect that the game does. So we'll grab these up here and then draw the shadow glyph pixel, and that would then be the Y position plus 1, because 1 further down, as well as the X pixel, 1 to the right. And since most drawing commands on any kind of computer graphics has 0.0 at the top left corner of the screen, adding one to the x-axis will move it one position to the right. Huh, interesting. All right, so this should take care of rendering both the, this one needs to be shadow pixel, and of course this needs to be the shadow color, not the forecolor. And shadow color, there we go. All right, so what happens here is that we start by drawing the shadow pixel if we need to. If we don't need to, then of course the entire calculation and the copy process will be skipped. But this will basically let us draw the glyph itself in the shadow color, and at the next pass around, if we need to render the actual glyph forecolor on top of it, then it will simply replace the previous shadow color that we put into the image buffer, and thereby overriding it, so we get the proper build-up of the shading sitting behind the actual text in front. So that should take care of that positioning. All right, so we still have a couple of things that we need to add in to get this working correctly. And that is the fact that at some point we will do things like strike through, we will do things like underline and bold, and those are situations that we also need to account for as part of this particular setup. And how do we go about doing that? Well, we kind of need to see if we can find, actually I think I made some screenshots, didn't I? Let's see. Did I put them up here somewhere? I honestly can't remember. That might be at the client actually. Let's see. Instance, vanilla. They may be here. This is a simple test. Okay. It seems I honestly can't remember. Well, whatever. Let's see if the wiki has some examples. It probably only uses, uses the built-in stuff. Okay. Well, we'll see if we can. Oh, actually, it's right here, I think. Yes. Let's see if. Whoa. Okay. So, let's grab this one and put it up here somewhere. All right, so if we look at this quick, we can see that the underline basically follows the entire glyph width, including the letter spacing for the entire chat element. We can also see that rendering strike through takes place at the let's see, 1, 2, 3, 4th pixel line from the top. So when we need to do the strike through, we need to draw an actual pixel there to correctly make the text rendered with the strike-through effect. For the bold, we basically need to do a duplicate of each individual pixel offset by 1. And the same goes for the shading, of course. So these three effects should be fairly straightforward to do. We'll save the italic rendering for later, because we need to do some additional offset stuff to get that drawn correctly. Okay, so we'll start by figuring out whether we need to do some bold, whether we need to do strike through, underline, stuff like that. All right, so if and that would then be the current chat element that we are rendering, which is chat elements e. So if chat elements e dot yeah, let's do bold first. Might as well. Bold is basically the same thing, except the pixel position is offset to the right by 1. So basically the same thing as this. This is C# under the .NET framework. The languages are somewhat similar. Most of these kinds of languages are all rooted in the original C structure and syntax, so there's not all that much difference between how C++ looks versus C# or Java or JavaScript or any of the other C type languages. For those that know C++, it should be fairly easy to jump into C# or Java or any of the other ones, because the overall syntax and name of methods and commands are pretty much the same. All right, so to offset this one, we need to add 1 to the pixel position, like so. That takes care of bold. Then we need to figure out, well, one of the major differences between C++ and the normal C is that in normal C you have an entirely different way of referencing properties as part of structures and such, and I believe it's a little bit different in C++ as well. In the .NET framework, if we yeah, let's do this one quick. As you can see, array copy, we use the period, whereas in the C and C++ structures we use the arrow setup, basically. It's the same thing, but those are the major differences. Other than that, syntax is pretty much the same thing. Okay, that takes care of bold. Next up, we'll see if no, actually, hold on a second. For the where did it go? This one. For the strike through and the underline, those are basically at fixed positions. So when we render the last well, actually, I am 100% self-taught, but I did start a long time ago. I don't exactly have any kind of formal computer science education as such. I learned it all the hard way by oh, here's a manual, go read the manual and see what you can make this do. That's basically it. But I would basically claim the stake that learning things the hard way is, for the most part, when it comes to code, learning it the right way. Jumping from Java to C++ shouldn't be all that big of an issue for you, since you already know a little bit of the syntax from Java. C++ is more complicated than working with C#, because if you step into C++ or regular C, you have to do all of your variable and all of your memory sanitization yourself. You have to do all the management yourself. Whereas in C#, you have a managed environment, which means doing something like this, for example, declare a byte array. This declaration basically tells the C# environment that I want a variable setup which needs this amount of memory, and it should be pre-initialized to basically have all zeros. When you do that in C++, for example, you need to pre-allocate that memory, and then you need to loop through and initialize all of it yourself. Otherwise, you will get an array full of junk. And in terms of releasing spent memory, you basically have to do most of the garbage collection and releasing yourself as well. So there's a lot more that you as a programmer need to keep track of in your code. If you don't, you will end up with a crashing application. You can very quickly and easily end up with an application that has a lot of weird behavior because you possibly forgot to pre-initialize some kind of variable or pointer. When you need to do stuff, a lot of the time you need to work with pointers instead of placing calls to methods and such. So you also need to do a lot of more referencing management in C++ versus C#. In C# you can do a lot of fire and forget stuff and then just move on. The major difference between C++ and C# is that C++ in every respect will win when it comes to performance. You cannot get anything faster than C++ unless you decide to write actual opcodes for the CPU in some assembly language, and that's about the most complicated thing to do. That's how operating systems were originally created, actually. That was way back before the time of graphical surfaces and such. Okay, back to the problem at hand. So for yes, for the strike through and whatchamacallit, the underline, there is actually no particular reason that we should go in and draw them for every Y position. So we will simply just draw them when we reach the last Y position, and then have the X counter take care of that for us. So in order to check for those, we kind of first need to figure out whether we are actually at the last Y position. So if the glyph Y position equals the glyph height minus 1, whoops, height minus 1, then we need to process the strike through, process strike through and underline. Now for underline and strike through, we do have one small issue that we need to contend with, and that issue is the actual line height as defined by our line height property. Now, for our default glyph setup, we are basically using these glyphs, which are 8 by 8 pixels each, at least for the most part. Some letters will of course only be 7 pixels tall to accommodate properly for how they should be drawn and such, leaving basically one transparent pixel underneath it. But as you could see in yes, all the code is available on GitHub, and I usually try my best to get the source code pushed to GitHub the same day as I do the stream, unless I need to do some bug hunting or documentation updating, then I might push or postpone the push to GitHub to the following day. But I usually get them pushed the same day. Links for the projects are available in one of the panels underneath the stream. Anyway, these glyphs are 8 by 8, and I set the line height default to be 9 pixels. The reason I did that was to accommodate the placement of the underline. Now, as you can see here, there is just 1 pixel between the bottom of the T and the underline down here, which would be the 9th pixel height. So when we calculate where to put the underline, we kind of need to work out whether that Y position is within the line height or not. We should probably also update the line height property to properly check that the line height basically is set to a height that can accommodate the glyphs if we want to force the basically the bitmap that holds the text to be fully visible. Alternatively, we can of course just do a check to ensure that the target position that we are using to basically draw the pixel is within the buffer size, and then allow the line height to determine whether part of the rendered glyph should be cut off. That way we can do, at least height-wise, do some text cutting. Okay, so here we need to work out whether we need to draw the blah 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 strike through, which would be the chat elements dot strike through. If that's enabled, if we have the underlined enabled, then we also need to process that. And again here we do end up in a situation where we need to account for bold as well as shadow. I'll do this quick just to separate them. So basically all the stuff that we're doing down here we need to more or less replicate for the shadows, except reference the shadow color instead. Now at the moment I'm simply just doing a copy paste of all this junk, which is not particularly efficient or good. Doing a lot of copy pasting basically just ends up with a lot of bloated code. So when I get to the point of replicating this entire setup for the 4 color pixels, I will basically migrate all of this into a method that we can call and then simply specify the X and Y positions as well as which of the 2 colors we want to use. In doing so, we build a comments code that can handle both the shadow and the foreground pixels and still position stuff correctly. Okay, so for strike through, we know for a fact that strike through needs to be on the 4th pixel as shown here, taken from the official wiki, and the underline needs to be at the 9th pixel, which is basically 1 pixel further down compared to the actual glyph height. So that's what we need to do now. As part of each of these, we also need to work out whether bold was enabled, because if it is both bold and strike through and underlined at the same time, then both the strike through and the underlined pixels need to be further extended by 1. Because doing the bold text is basically just grabbing the existing glyph and redrawing it offset by 1 pixel to the right. That's something that we need to replicate as well. Okay, so for this, again, we need the target position and we also need the copy. So we'll grab another copy of these, and yes, I will optimize these as well. Here, this would then, instead of being the actual pixel Y position, we kind of need to calculate where we need to put this, because if we just put it as the 4th pixel and the glyphs end up having a size of 16 by 16 pixels, then the strike through will basically be incorrectly positioned. So how do we calculate this? Well, we will go up here and do a pre-calculation of that particular position. That way we don't have to do the expensive math every time, and we can simply just reference a value. So that would be the strike through Y. And the way we calculate this is we know that the glyph has a height of 8. So if we basically grab 8 divided by 2 makes 4, and then we need to subtract 1 because we are 0 based. So the actual positioning of it should be fairly simple. We'll grab the surface size height divided by 2 and subtract 1. And just to ensure that we don't end up at a negative position, we shouldn't ever, but we could put in some sanitization math or checks just to make sure that it doesn't become a negative value. It shouldn't ever, but it can be done. All right, so this would then, for the strike through, we need to use the strike through Y instead of the pixel Y, and then this would be the regular pixel position for it, and there we go. Added to this, of course, we also need to do the check for the bold and then draw it again, and this time of course offset by 1. So if this one is bold, then do this once more, except increase the X position by 1. There we go. That takes care of strike through. As you can already see, Um, as you can already see, there have been a number of basically copy-paste of the same piece of code done throughout this setup. So when we do the optimization of this, we'll do something that at least to some extent takes care of this particular replication. All right, so for the underline, here we need to calculate, or rather place the pixel basically 1 pixel underneath the total height of the glyph. So the Y position shouldn't be all that difficult to calculate because it's basically just the glyph height plus 1. And again, this needs to be done for bold as well. So we'll grab a copy of this and specify the glyph height. And of course plus 1, like so. And the same goes for the bold addition. There we go. All right. So yes, that takes care of both underlined and strike through. We still need to add in italic. At least at some point we need to. Let's see, yeah, that would be the regular, yes. However, doing the italic is a little more complicated, especially when we do the basically the double up of the font image. If we do the double up, we can use basically half pixel offsets to render the font more nicely. As you can see from this image, the top part of the text is offset by 1 pixel, which basically cuts some of the glyphs into pieces, making them look not particularly good. This is the way the game does it by default, and this particular setup we would probably need to do as well when it comes to rendering at normal size. So this would be one scenario of italic rendering, and in doing the double up we need to do it in a different way. It is for editing the MOTD and doing custom in-game warning messages to players before the server restarts or does a maintenance shutdown. So we can see in the launcher what the text will look like without having to A, launch this game server, and B, launch the game client, and C, connect to that server to see those messages. This is simply to let us do that editing before we actually start up all this stuff regarding the game itself. That's the main reason. I mean, one of the biggest issues in doing anything Minecraft related is that you changed a single setting there. Okay, you have to shut down all the game clients that are currently connected and shut down the server and start it up again just for that one setting to take effect. And if you're basically going through setting up custom messages for something, then A, you need to do it at a time of day where there are not that many players on the server. So you can do the text customization and get it set up correctly. or hope to God that whatever custom text you put in there works when it's supposed to be shown, and then basically let it run. Um, I have in the past run several successful Minecraft communities, and know from bitter experience how much extra work it takes to get, say, player ranks, and rank tags and custom player colors and such working, as well as, say, advertisement texts that show up in chat, asking people to go donate to help keep the community running, for non-profit communities and so on. And all in all, you can very quickly, and this is no joking, you can very quickly waste an entire day, 10 or 12 hours, just configuring those. Um, Even if you have a test server set up. So part of why I'm doing this in this launcher is simply to avoid that particular issue, because it does take quite a while to start up the server, connect with the client, do the tests, shut it all down, make the changes, boot it all up again. Um, by adding this straight into the launcher itself, and having it replicate exactly what the game does, we can pre-configure this without having to fire up Java and shut it down 10 times just to get the customized texts rendered the way we want them to. So just a convenience tool, I guess. It's strictly not needed for the launcher itself, but it does make life a lot easier. Um, Again, one particular situation where this font rendering comes in handy is in terms of creating the customized text, warning texts that will go in the game chat before restart or backup. Um, if I didn't put this in the launcher, we would actually have to sit there and wait for the scheduler to get to the point where it needs to dump the message in chat, or do some other shortcut setup thingamajig to get those texts dumped in the chat so we can see that they render correctly. This just makes life easier. Granted, it's a little more blah, building up this stuff for the launcher application, but once it's built, it's basically reusable. So um, all of it just for convenience. Okay, so next up, we need to optimize this for use with the both the shadow and the foreground stuff. But I think I will take a quick couple of minutes break, get my nature call sorted and all that stuff. So I shall be back shortly, and smoke 'em if you got 'em.